Hi, everybody. It's Professor Mitchell. We are continuing with Chapter 6. So this is the last section that we cover in Chapter 6, Section 6.6, Normal as Approximation to Binomial. So remember in Chapter 5, we talked about the binomial probability distribution. We used the pop quiz as an example for that. We did the little pop quiz experiment. And then we calculated all those probabilities. What's the probability of getting 3 right by guessing? Okay. So what we're going to talk about now, and this bullet here, we really start to kind of get into details. So presents a method for using a normal distribution as an approximation to the binomial distribution. That's all we need to know right this second. I'll tell you all this other stuff later. Okay, but remember that the binomial probability distribution is discrete. It only takes on whole number values and a finite number of them. But the normal approximation is continuous. So one of the concepts that you have to get used to when you use the normal approximation to approximate binomial is that you have to do this continuity correction. So I'll explain how I like to do that when we get there. Okay, so pop quiz, just kidding, we're not going to take another pop quiz, just using that as an example. Suppose that you take a 20-question true-false test and you guess at every question. So the first thing we're going to do is use the binomial probability function, the binomial probability distribution, to find the probability that the student gets exactly 14 questions right. Exactly 14 out of 20. So if you'd like, go ahead and pause the video and see if you can remember how to do that. That's from Chapter 5. And then we'll compare notes here when you're ready. Okay. So that probability from that formula that we talked about in Chapter 5 would look like this. So we called that formula P of X. So in this case, X is 14, N is 20. The identical trials are the 20 questions. And P is 0.5 because when you randomly guess at a true-false question, you have a 0.5 probability of getting it right, which means you also have a 0.5 probability of getting it wrong, right? Remember, Q is 1 minus P. So that probability comes out to about 0.037. 0.037 probability of getting exactly 14 questions right. Okay. But one of the biggest challenges in statistics is not only answering the questions correctly, but also coming up with the right questions. Okay. So if I'm a student in this class, and let's say I forgot I was taking the class and I show up week 12 and all of a sudden there's this 20-question true-false test. I don't know anything about the subject, so I have to guess. Well, yeah, it would be nice if I got exactly 14 right. Okay. But is that the only good outcome? That's the question. So think about, why did I pick 14, first of all? 14 out of 20 is 70%, right? So this is the probability of just barely passing, But when I'm worried about a big test, I'm not worried, what's the probability I'm just barely going to pass. I want to know what's the probability I'm going to pass, right? So yeah, it would be nice if I got 14 right, but it would be even better if I got 15 or 16 or 17, 18, 19, 20, right? Any of those outcomes would be good, okay? So one of the things that we can use this section for is figuring out an easier way to figure out that probability, because if I use this formula, that's going to drive me crazy, because I'm going to have to do P of 14 plus P of 15 plus P of 16 plus P of 17, 18, 19, 20, okay? You could get it done, all right, take you a few minutes. but I think there's an easier way, okay? And by the way, we do have something called Table A1. We talked about it briefly back in section 5.2. Unfortunately, Table A1 wouldn't help with this problem either because it only goes up to n equals 15. So that's not going to help. Okay. All right, so here's the idea. It turns out that you can use, under certain circumstances that we're going to talk about here pretty soon, you can use normal distribution to approximate binomial probabilities. So what I have here are some pictures of binomial distributions. This one is n equals 10. P equals 0.2, so imagine a 10-question quiz where every question has 5 choices. And that distribution looks like this. It's a little skewed to the right. Does not look particularly normal, right? It's not symmetrical and it is skewed, okay? But when I bump up the number of questions, say, or the number of trials, say to 20, now it does start to look a little more normal, especially if you ignore these outcomes over here that, you know, have almost no chance of happening, okay? That looks a little more normal. And when I bump it up to 100, that looks really normal. That looks really normal, okay? So it looks like as long as n is large enough, these binomial, you know, histograms will start to look normal. And that's pretty much, that is pretty much the story. It's not exactly just n being large enough. It's actually a combination of n and p working together. Okay? So first of all, just a quick review of binomial probability distribution. Remember, it has a fixed number of trials that are independent. Okay, so success on one trial does not affect your probability of success on the next trial. Each of the outcomes from a trial are in 2 categories called success and failure. And the probability of success has to remain constant. So if I'm going to use this example of a multiple choice test or a true-false test, I have to stick with the same number of choices for every single question. Okay. And then remember the notation, n is the number of trials, x is the number of successes, p is the probability of success in any one trial, q is the probability of failure in any one trial. So q is 1 minus p. Okay. All right. So here's an example. I can't remember if we've looked at this example before. It says we saw in a previous section. That could have been a section that we skipped. The sampling distribution of a sample proportion tends to approximate a normal distribution. That might have been in section 6.3, actually. I can't remember. So Mendel's experiment, he was a famous geneticist. From what I remember, he sort of the study of genetics kind of started with him. He was one of the first people to study it. So he was growing pea plants, and he had 580 of them, and he expected 25% of these peas to be yellow, okay, based on genetics. But when he did the experiment, he actually got 152 yellow peas, which is 26.2%. Okay. So if you think about the histograms that I was showing you on the few slides ago, this is what that binomial histogram would look like if n was 580 and p was 0.25. It looks very, very normal. Okay. So what we're going to be looking at in one of these examples later on is 152 yellow peas an unusually high number? Or is it not surprising that I would get that many? Okay. All right. So very important. These are the requirements for using the normal distribution to approximate binomial. Number 1, your sample is a simple random sample of size n from a population in which the proportion of successes is p. And Very, very important, because remember that first histogram I showed you, it didn't look all that normal. And that's because this requirement here was not satisfied. In order for this normal distribution to give you a good approximation, n times p and n times q both have to be at least 5. So if those requirements are satisfied, then the probability distribution of the random variable x, which is a binomial random variable, can be approximated by a normal distribution with these parameters. Remember, for a normal distribution, you need to know what the mean and the standard deviation are. So the mean would be n times p, which, by the way, in section 5.2, we talked about that is the expected value of the binomial random variable. It's n times p. And the standard deviation is also the same. It's the square root of n times p times q. All right, and then lastly, when you're using normal approximation for binomial, you have to do this continuity correction that I mentioned earlier. And I will show you how to do that when we get to our examples. Okay, this right here is not my favorite way to explain this. Okay. All right, so here's your procedure. You check your requirements. N times p, n times q are both at least 5. Calculate the mean and the standard deviation using those formulas. And then figure out your continuity correction, basically. Okay, so here's an example finally. In one of Mendel's famous hybridization experiments, he expected that among 580 offspring peas, 145 of them, which is 25%, would be yellow. But he actually got 152 yellow peas. Assuming that the 25% is correct, what is the probability of getting 152 or more yellow peas by random chance? Okay. And then based on that, we can figure out, is 152 a significantly high number of yellow peas? Am I surprised, or would I be surprised if I got that many? Okay, so the first thing we're going to do is check our requirements. Remember, n times p and n times q both have to be at least 5. So n is 580, p is 0.25. N times p comes out to 145, which is definitely at least 5. And n times q is 580 times 0.75, which is 435. Okay, so this is a really, really good problem to use normal approximation. Okay. All right, now we'll find mu and sigma. Mu is n times p. That's the thing we just checked to see if it was at least 5. That's 145. And then for sigma, if you do square root of n times p times q, the square root of 580 times 0.25 times 0.75 comes out to about 10.4283. Okay. So in my calculations, I might use 10.43, or I might go with 10.4283 if I'm worried about rounding. All right, so we want the probability of at least 152 yellow peas. Remember, again, binomial is a discrete random variable. And so the relevant whole number in this example is x equals 152. So what we're getting ready to talk about now is the continuity correction. And I have drawn my own picture for that. I have my own system for the continuity correction. It really works for me. Hopefully it'll work for you. What I do is I just draw a little part of a histogram. I imagine that this is part of my binomial histogram. And I always put the relevant number right in the middle. I just put 3 numbers: the relevant number, the number that's 1 less, the number that's 1 bigger. Okay. So if it says 152 or more, I look at the numbers 151, 152, 153, and I say, okay, in the event 152 or more, is 151 included in that? And it's not, right? And then I ask, is 152 included in that? And the answer is yes. 152 or more includes 152. And it includes 153, 154, and every bigger number, okay? So the idea behind the continuity correction is that if you imagine a normal curve sitting on top of this histogram, okay, then the part under the normal curve would actually start at 151.5, all right? This whole bar represents 152. This whole bar represents 151. And so if I want to start in the right place, I'm going to start at 151.5. All right, so top picture you see here is my binomial histogram. You do not have to draw this, all right? Notice it really does look normal. Notice that they have the one bar highlighted that represents 152. They're showing you that it starts at 151.5. Don't even pay any attention to this 152.5, okay? So when I turn that into a normal curve, I'm looking at in a normal distribution where the mean is 145 and the standard deviation is 10.4283. What is the probability that X is greater than 151.5? This is a spoiler right here. Don't pay any attention to that. All right. So maybe this would be a good time to ask you to pause the video. Think of this as a section 6.2 problem now. We did problems like this in section 6.2. All right. So remember, you turn this into a standard normal distribution, figure out the z-score that goes with 151.5, and find that probability. And when you're ready, come back and we'll compare notes. All right. So again, you have to translate this thing into a standard normal distribution. I personally, I didn't notice that this wasn't already done. Even after I translate it to a standard normal distribution, I still like to draw the picture. So the picture looks something like this. Okay, so if this is a standard normal distribution, that means along the bottom here are all z-scores. 0 is right in the middle. The z-score for this 151.5 comes out to 0.62, which is over here somewhere. Okay. So now, and remember, we're looking for the probability that z is greater than 0.62. Okay. So if I go to my table, which I have open over here, and I go to the positive side of the table. Here is 0.6. I go over to the column with the 0.02 on top. I find an area of 0.7324. Okay. Is that my answer? No, that is not my answer because that is the area to the left of 0.62. Table always gives you area to the left. Okay. So that's why it's such a good idea to draw the picture. As soon as I draw this picture, I see that the probability is going to be less than half. Okay. So it's not going to be 0.7324. It's going to be 1 minus 0.7324, right? Okay. So this probability here, or this area here, is 0.7324. Which means the area to the right is 1 minus 0.7324, and that's how they get this 0.2676. 0.2676. That is the approximate probability of getting 152 or more yellow peas. Okay. All right, so remember the other question they had about that, is that a significantly high number? Would I be surprised to get that many? Well, no, I wouldn't be surprised. All right, the way that we've been defining a significantly high or significantly low number of outcomes is if the probability of getting that many or that few is less than 0.05. Less than a 5% chance of getting that many or that few. There is better than well, it's a 0.2676 chance of getting 152 or more. That would not be unusual or surprising. So 152 would not be a significantly high number. Okay. I could easily see getting that many, even if it's true that 25% is the correct proportion. Okay, more about the continuity correction. I really like to draw the picture. You know, the little piece of the histogram, you color in the bars that are included in your outcome, you leave out the ones that aren't. So I have never really felt the need to think about all these different examples because they just, if you draw the picture, you'll see this, okay? At least 152, that's the one we just did. That's another way of saying 152 or more. More than 152 would not include 152. So you'd be able to figure out all this stuff just by drawing the picture. Okay. So I think I have at least one more example where you can see that. Yes, here we go. Using the same information from the previous example, let's find the probability of getting exactly 152 yellow peas. Okay, so that is given n equals 580, assuming that p is 0.25. What is the probability of exactly 152 yellow peas? And then they're asking, is this result useful for determining whether 152 yellow peas is significantly high? Is that the useful thing to be looking at? It kind of reminds me a little bit of the pop quiz question I asked you at the beginning. Okay. Probability of exactly 152 yellow peas. Okay, so the mean and the standard deviation are still the same because I haven't changed n and p. So here is the histogram that I drew to help me figure out the continuity correction. So out of the numbers 151, 152, 153, exactly 152 only includes 152. Okay. So if I draw if I think about drawing a normal curve over top of this, it would go from here to here. It would go from 151.5 to 152.5. So if I draw my normal curve like this, it's a really skinny area under the normal curve. All right, so works kind of like the last one. Again, I like to draw the picture of the standard normal distribution. It doesn't have to be a great picture. Oops. It's normally a little better than that. So here's 0 right in the middle. The z-scores for 151.5 and 152.5 are 0.62 and 0.72. I don't worry as much as they do about making everything proportional. It'd probably be easier just to type these, but okay. So then you color in that region between 0.62, 0.72. And this is the situation we've talked about a few times. You look these two numbers up in the table and then subtract the areas, right? So the area to the left of 0.72, that's the 0.7642. The area to the left of the 0.62, we already knew that was 0.7324. So to find the area between the two z-scores, you just subtract those. So the probability of getting exactly 152 yellow peas would be 0.0318. Okay. So it would be kind of unusual to get that exact outcome. However, if you're asking the question, is 152 significantly high? That is the wrong question to ask. You would ask the question that we asked earlier. What is the probability of getting at least 152? Just like the pop quiz example at the beginning. You know, getting 14 right out of 20, yes, that would be nice. But if you're just trying to pass, you want 14 or more right. Okay. So again, if you're trying to figure out is 152 a significantly high number, you look at the probability of 152 or more. Okay. In general, the relevant result is the probability of getting a result at least as extreme as the one you obtained. So at least as extreme means at least as high if you're looking at significantly high, or at least as low if you're looking at significantly low. Okay, so I'd like to end this section by going back to the pop quiz that we talked about at the beginning, the one that has the 20 true-false questions. We used the binomial formula to find the probability of getting exactly 14 questions right. So one thing that I like to do whenever I find a new way to do an old problem is see, okay, well, how good of an answer do I get? All right. So hopefully I'll get something pretty close to 0.0370, which is what you get from the formula. And now we can answer the more interesting question, the more relevant question. What is the probability of guessing at least 14 questions right? And we don't have to drive ourselves crazy by doing P of 14 plus P of 15 plus P of 16 all the way up to P of 20. We can use the normal approximation. Okay, so I would like you to try both of those if you're watching at home. Pause the video and then we will come back and compare notes. Okay, so I thought the easiest thing to do would be to handwrite these instead of driving myself crazy trying to type them. So the first question is the probability of getting exactly 14 right. This is now using the normal approximation. So n is 20, p is 0.5. So the first thing I'm going to do is check my requirements. Is the normal approximation going to give me a decent answer? Well, yes, it should, because n times p is 10, which is at least 5. And n times q is 10, which is at least 5. Okay. So I'm going to use a normal approximation. U is n times p, which is 10. Sigma is the square root of n times p times q. N times p times q is 5. Sorry about my little scribble there. The square root of 5 is about 2.24. Okay. So when I get ready to sketch my normal distribution, again, imagining my normal curve fitting over this histogram. Exactly 14 means exactly 14. It does not include 13, does not include 15. So when I shade under my normal distribution, I'm going to shade between 13.5 and 14.5. Okay. So here is my normal distribution with a mean of 10. I'm looking for the probability that x is between 13.5 and 14.5. So when I change that into a standard normal distribution, the z-score for 13.5 comes out to about 1.56. The z-score for 14.5 comes out to about 2.01. So here is my standard normal distribution. Let me just point out what I've been trying to get into the habit of doing lately is when I have some other normal distribution, I call that random variable x. And when I'm doing standard normal, I call that z. It's kind of a new thing I've been doing. Okay, so the probability that z is between 1.56 and 2.01. Again, we're going to look up those areas in the table and then subtract. The area to the left of 0.9778 is, the area to the left of 2.01 is 0.9778. The area to the left of 1.56 is 0.9406. So I subtract those and I get 0.0372, which is kind of exciting because remember the answer from the formula was 0.0370. So that's really, really close. That's a really good approximation. Okay. Unfortunately, it's not the interesting question. If I'm guessing at a true-false test, I want to know the probability I pass, not the probability that I barely pass. So here in number 2, under this line, mu is still 10, sigma is still 2.24. So the difference now is I am interested in the outcomes 14, 15, all the way up. It was at least 14. So I'm going to start at 13.5, everything to the right of 13.5. As a standard normal distribution, that becomes the probability that z is greater than 1.56. And I already know the area to the left of 1.56. It's this 0.9406. So the probability that z is greater than 1.56 is 1 minus 0.9406. That is 0.0594. Okay. So if you randomly guess at a 20-question true-false test, the probability that you will pass is almost 6%. Which is why if I ever gave you a true-false test, I would either ask you to share your work or I would ask you more than 20 questions. Because actually that doesn't even fall into the unusual category, does it? Okay. 14 right answers would not be considered significantly high by our definition, because that probability is greater than 0.05.